Let's study 10th standard ICSE Physics, Chapter 4C, Applications of Refraction of Light. Why does a stick or a pencil appear bent at the surface of water? Why does a coin kept at the bottom of a bucket full of water appear to be raised? Well, it's all because of refraction of light. Because of refraction, the apparent depth is different from the real depth. You see, point P is the actual tip of the stick, and the real depth is so much. But since it appears to be raised, and I'll explain shortly how, but since it appears to be raised, we perceive it to be at a smaller depth, which is called the apparent depth. So whenever we are viewing something in a denser medium, that is, the ray of light is moving from denser to rarer, remember, it appears to be raised. That is, the apparent depth is less than the real depth. Here, in this diagram, which is double-ticked, we draw two rays. One, just draw it perpendicular, so no refraction. And the other one will bend away from the normal, so it appears to be coming from this point. So if there is a coin out here, we will perceive it to be coming from here. That means the coin is appearing raised. In fact, the entire bottom floor of this swimming pool or bucket will appear raised. Now, ideally, these two rays are not so far apart. They are very close to each other and both of them enter the eye. But for clarity, we have drawn it so far apart. So the same logic causes the bending of the stick. So we draw two rays and both of them bend in such a way that they appear to meet at a point just above P. And then this happens at all these points, which we don't have to show. So the bending happens exactly at the boundary separating air and water. So let me draw this diagram to show you how it is to be done, because even this is double ticked. I'm not using the ruler or pencil, but you should. So assume this is the boundary separating the two media, and this is a stick or a pencil. So this is point P. I draw the image beforehand. I know it is going to be raised, and draw the bent pencil. Bending is exactly at the surface. So I draw this first and then draw the rays. This way you will never make a mistake. So from here, draw two rays, 1 and 2. Arrows are important. Now join this and this with ruler and just extend it. Similarly, join this and this with ruler and just extend it. And finally, draw the eye. Make sure the lashes look beautiful. So this is how the diagram is to be drawn. Remember, the rays are towards the eye. Don't draw the arrows away from the eye. We don't release light. Only Superman can release a laser from his eye. On the other hand, if you were inside the swimming pool or the water, you will see that the objects are farther away. The opposite has happened, because now when light travels from rarer to denser, it bends towards the normal. Here just one ray is used, not two. That is why the fish think that you are taller than you actually are. Again, the rays should be towards the eye. So this is the reason why when you are fishing with a harpoon, the fisherman or the hunter would always aim in such a way that he is able to catch the fish. He may be aware that the fish that he perceives is not at the actual position, but the fish is raised. So accordingly, maybe he will aim at the tail so that he can hit the head, depending on in which way the fish is located. This is also the reason why if you see a blue bead at the bottom of a river, and if you immediately try to lift it, at first you might miss catching the blue bead because of refraction. Now there are some formulae which we need to remember. Refractive index is always real depth upon apparent depth. And the shift, that is the difference between the real depth and apparent depth, this shift has another formula, real depth into 1 minus 1 upon refractive index of water or of that substance. This shift, that means by how much will the object appear to be raised, depends on three factors. Again, so many factors. It depends on refractive index. More the refractive index, more will be the shift. Understand, it's a fraction totally. So the net effect is more the refractive index, more is the shift. Second, it depends on the thickness of the denser medium, which means how deep is the water. The deeper the water, the more will be the shift. And third, it depends on color or wavelength. No prize for guessing. Red will shift less and violet will shift the most, simply because the refractive index for violet light is the most. And interestingly, the refractive index 3 upon 2 gives us some information. For glass, if the refractive index is 3 upon 2, it means that the glass slab appears only 2/3 of its real thickness when it is viewed from air by keeping the eye vertical above the slab. Assume that this was a glass slab and you were viewing from top. You will notice that if this entire height was 3 centimeters, but for you the glass slab would appear to be only 2 centimeters deep. Similarly, for water the refractive index is 4 upon 3. That means the 4 will represent the real depth and 3 will represent the apparent depth. So if you were looking at your own legs, and suppose your legs are 4 feet long. Wow, good opportunity to be a model then. 4 feet long legs, but in water you will feel that they are just 3 feet long because there has been a shift. That's the advantage of knowing the refractive index. And this is the formula we just used. Refractive index is real depth upon apparent depth. Now there are some consequences of refraction of light. First of all, why does a star twinkle in the sky? Well, that's because there is a change in refractive index of air with temperature. The apparent position of stars keep changing as the refractive indices of the atmosphere's layers keep changing. So there are various layers of the atmosphere which are not visible, of course. And here's you gazing out in the night sky, and here's your star. And you're singing a song, twinkle, twinkle, little star, but you'd wonder, why is it twinkling? The reason is, first of all, when rays of light travel through the atmosphere, it suffers some refraction. Various refractions happen because at every layer, the density is different. So you feel the apparent position of the star was here. But every second, since the layers, the wind keeps moving, the refractive indices keep changing. After a fraction of a second, now the path taken by the light is a bit different. And now you feel that it has come, let's say, from here. So every moment, the position of the star keeps changing. This flickering gives you the twinkling effect. Similarly, when you look at the sun, even though the sun has not yet risen, you may feel that it has, because the rays of the sun, which were going to miss your eyes, actually bend towards you and they reach your eyes. And you can see the apparent image of the sun. You feel the sun has risen a few minutes before it actually has. But what you're seeing is the raised sun. It's just an illusion. This is the image of the sun because of bending towards the normal, as it is moving from the rarer layers of atmosphere to the denser layers of atmosphere as it reaches your eye. Same can be said about sunsets. Even though the sun has set, you still feel that it is up for a few extra minutes because you are looking at the apparent image of the sun, not the actual sun.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.